Perestroika, and the topic of my lecture today, or at least the title of my lecture today, is The Mystique of the Loop. Unfortunately, this lecture isn't about mystiques, and it's not about loops either. I changed it. As I developed this lecture, am I getting fuzzy coming out the end there?
Yeah.
I'm talking too loud, aren't I?
Smooth the mic down.
Yeah. I'm sorry, I got a big mouth. It's hard for me to tone down. Still kind of fuzzy, isn't it?
It's been that way, so down more.
Just put it all the way down. It's really a good mic.
Okay, let's move it way down. There we go. I can't help but talk loud. Okay, as I developed and refined the lecture, I expanded it and changed it, and it grew until finally I ended up with something much different from my original intention. So what I really want to talk about today is a loose analogy between the structure of a computer program and the structure of a computer game. And the basis of this analogy is, or the starting point for this analogy, is this diagram right here. I call this a game tree, and it represents the flow of the available states as a player moves through a game. So the player starts off the game at the top of the game tree, right up here. He's in a given state. You're a young prince with a sword and a future, and he has some options. So he selects an option, and that takes him to a new state. This creates more options. So now he selects one of the options, and that takes him to another state with more options, and more, and on and on and on, until he reaches the bottom of the game tree, which is the end of the game. And he's in an end game state, which is either winning or losing. And that's the game. You know, would we be better off with this thing just shut off?
Right.
Okay. Well, that's great. So anyway, that is a game tree, and it's the fundamental architecture of all games. Now, let me show you another structure. That's a program tree. This is what a computer application uses. For example, take a word processor. The user, the player has been transformed into a user now. The user starts at the beginning of the word processor with a blank sheet of paper. That's the state he's in. He has some options. He types a letter. That's one of his options. So he types the letter C. That takes him to a new state. A blank piece of paper with the letter C on it. He now has some more options. He selects another option. He types the letter A. That takes him to another state. A piece of paper with the letter CA. Now he has more options. He selects an option. That takes him to another state. A piece of paper with the word cat on it. And on and on and on until he reaches the end of the program tree. He has a document. That is the final state for the program tree. So, in the program tree, the user navigates through the tree to select the document he desires. This is an interesting point. Users don't create documents in word processors. They select them through a sequence of commands. They navigate through a tree to get to the document that they want. Now then, you will note that there's an interesting similarity here. These two structures look very similar. All you have to do is cut and paste, you know. So gee, that's very suggestive. We have two very similar structures going on. Golly gee, doesn't that suggest something to you? Well, yes, games and programs are very similar. But at this point, I'm going to switch gears on you and say, yes, they're similar, but they're different. How are they different? Well, they're different. There are a lot of differences, but one difference I immediately leap upon with gusto is the fact that word processors, for example, work and games don't. Specifically, take my word processor. I use Microsoft Word 4.0 on a Mac 2X. I'm very happy with that program. It's and I'm not making a commercial for Word. We could use Full Ride or Right Now or any other word processor, and I would probably be very pleased with that word processor. It does everything I want to do. I have no problems using it. It's got all the capabilities I want. It's got features up the wazoo. It's got features that I don't want. It's got more stuff than I could ever possibly use. So I'll tell you, I'm really happy with the state of my word processor. Not so, games. Let me tell you about my favorite game right now. Their Finest Hour, Battle Britain. Love that game. Lots of fun. It is full of flaws and deficiencies and defects and errors and problems and difficulties. I could tell you a million things wrong with Battle of Britain. Now, at this point, and I want to reassure you, I really like the game. It's a great game, but it's full of problems. Now, you might say, well, Chris, this is unfair. You're a professional computer... Oh, wait, I'm sorry. I've made a mistake. You might say, Chris, this is unfair. You're a professional computer game designer. You, of course, can see all of the structural defects in a computer game, but in a word processor, you're not a professional word processor designer, so of course you won't see the defects there. Well, my answer to that is, wait a minute. I use word processors all the time. I've written a number of books, many essays, articles, letters. I put out the Journal of Computer Game Design. I put out tons of documents on my word processor. In fact, I'll tell you, I spend more time in my word processor than I spend playing games. So I think I can say there's a real difference going on here. The satisfaction that I feel, the difference in satisfaction that I feel for word processors over games reflects, I think, a very serious discrepancy. I think we can safely say word processors do their job better than games do their job. And I offer this not as a negative observation, but as an observation of opportunity. Golly gee, if we can just figure out what they're doing right that we're doing wrong, well, maybe we can make our games better. So let's see if we can examine the difference between these two. And to do so, I'd like to introduce you to two new concepts. The first concept I want to talk about is the set of accessible states in a tree. That is, all of the states at the bottom of the tree. That constitutes the set of accessible states. Those are the states that the user can actually access, the ones he can reach with this particular program. The documents that he can really get, or the games that he can actually play, and the things that he can actually do in those games. That's the set of accessible states. The second concept I want to introduce you to is the set of imaginable states. All the states that you could reasonably imagine accessing with this game or program. In other words, all of the documents that I might want to make, all of the games that I might want to play. Now, let's talk about the ratio of the sizes of these two sets. The number of accessible states compared with the number of imaginable states. How am I doing back there? Can you guys hear me clearly? Okay, good. So the number of accessible states compared with the number of imaginable states. Now first, there's a simple observation. Every accessible state is imaginable, but not every imaginable state is accessible. There are a lot of, anything I can access, I can obviously imagine. But things I can imagine are not necessarily accessible. Therefore, the set of imaginable states is always larger than the set of accessible states. But there's another observation I'll make, and that is that the ratio of accessible states to imaginable states is an index of quality for the product. In other words, the closer that ratio is to 1, that is, the more accessible states I have relative to the number of imaginable states, the better the product, be it word processor or game. And let me substantiate that by hearkening back to what I was saying about Microsoft Word. Why did I like Microsoft Word so much? Because anything I wanted to do with Microsoft Word, I can do. In other words, any state I want to access, any state that I can imagine and desire, I can achieve, I can access. Therefore, what I'm saying about Microsoft Word is that I like it because the ratio of accessible states to imaginable states is very close to 1. Whereas, with games, there are all sorts of situations I get into where I'm sitting there inside that HE-111 saying, "No, he's gonna get me, I'm out of ammo! Yeah! Yeah, crash!" This is not how I imagine the game coming out. And so I'm dissatisfied. there are all sorts of situations where I'm saying, wait a minute, why can't I be 5 places at once? It's unfair that I can only shoot one machine gun at one time. There are a million things I'd like to be able to do in that game that I can't do. There are lots of imaginable states that are not accessible. Therefore, the ratio of accessible states to imaginable states with games is low, and that's why I'm dissatisfied with them. Well, I haven't proven anything here, but I think we have a very interesting hypothesis that the ratio of accessible states to imaginable states is a good criterion, a good rule of thumb for gauging the success of a game. So the next question then is, how can we increase that ratio? How can we improve our games by increasing the ratio of accessible states to imaginable states? Well, there are 2 ways to increase a ratio. 1, increase the numerator. 2, decrease the denominator. In other words, you can either have more accessible states or less imaginable states. Now, let me talk about that second one first. How can we decrease the number of imaginable states? At first glance, that sounds really silly. I mean, do you even want to do it? And if you could do it, how could you cut your user's imagination short of a frontal lobotomy? And that doesn't sound like that. We don't control our players' imagination, so there's no way we can decrease the number of imaginable states, is there? Well, no, that's not true at all. We can decrease the number of imaginable states very easily. This is the most fundamental, the most elegant form of design. It is what the level of design that goes on long before you begin programming. It is a matter of setting the context of your game. Context defines the number of imaginable states. For example, how many times have you been in the middle of a hot game of tic-tac-toe when all of a sudden your opponent leaps up from the table and says, "God damn it, I want to chop the monster's head off"? Well, that's ridiculous. That's absurd. You can't chop the monster's head off because there is no monster in tic-tac-toe. So you can't even imagine the possibility of chopping his head off. Or how many times have you been playing chess and your opponent reaches into his pocket, pulls out a pair of dice, blows on them, shakes them a few times, rolls it on the ground and says, "Hot ziggity, snake eyes, checkmate." That doesn't happen because chess is a deterministic game. It is a game of pure skill. There is no element of chance in game. So, in the game. So the concept of rolling dice is unimaginable during the play of a chess game. Therefore, people don't imagine it. It is not one of the imaginable states in chess. Chess has a tightly defined context. That is an extremely important concept in game design. Creating a game universe that is closed, not open, closed, consistent, and complete. This is one of the most fundamental mistakes made by game designers over and over and over again, and it is their overweening sense of grandiloquence that trips them up here. The classic problem is game designer starts off, says, "Boy, I'm going to design this game. This game is going to be so great. It's going to be fabulous. By God, my game is going to have stars and galaxies and exploding planets and TIE fighters and little puppy dogs that wag their tails and prostitutes with hearts of gold. And boy, my game is just going to have everything in it." This is the wrong way to design games. Because every time you add a feature, you're going to add a couple of accessible states and zillions of imaginable states. Example. Here you are designing your game, you come up with this neat idea. You put a couple of pieces of flint on the ground somewhere in the game. And what your plan is that the player will notice the pieces of flint, pick them up, strike them against each other to make some sparks, then he'll blow gently on some sawdust, get a fire started, get the fire roaring, and then use the fire to light the torch. And then he can take the torch into the dark cave so that he can see what's happening. How clever of you. You put fire into your game. Of course, what's to stop the player from using the fire as something to scare off the wild animals so he can sleep at night without being eaten? You didn't think of that, did you? Or what's to stop the player from using the fire to harden a sharpened stick so he can take on the woolly mammoth by himself? Or what's to stop the player from using the fire to start a fire at the north end of town so all the townspeople will run to the north end of town to fight the fire, and he can run to the south end of the town and steal the gold? Didn't think of that either, did you? What's to stop the player from burning down the front door that's locked and that he can't get past because he can't find the key? What's to stop the player from using the fire to burn down Dracula's castle so he doesn't have to screw around with Dracula anymore? What's to stop the player from setting a forest fire that would burn down the big forest so he never gets lost in the maze in the forest that he created? There are a million things those people can come up with. And all those imaginary things people can cook up, you're only going to be able to implement a tiny handful. In other words, when you stick in a feature, you're creating lots of imaginable states and very few accessible states. That's the wrong way to design games. What you want to create, yes, you want to create a universe, but it's got to be a closed universe, a complete universe. Everything inside the universe has to work the way people expect it to work. That means what you really want is parsimonious design. You don't want grandiloquence. You don't want to be throwing everything into the game. That's humongous heap game design. Let's keep piling the shit on higher and higher, and if we let it sit long enough, something good will come out of it. Well, that may work with compost heaps, but it doesn't work with games. So try to go for a closed and complete game universe. That way, you are narrowing the range of imaginable states well, you're narrowing the range. The user interface manifestation of this problem is the parser. The parser is a disaster when it comes to games. The basic problem with the parser is a parser creates the imaginable state. Anything you can say in English, it can understand. That is the promise, the implication of a parser. I mean, you type some English in it. Therefore, anything I can say, it can understand. Well, of course, that isn't true. In fact, we all know that the number of accessible states, the number of states a parser can understand, is an infinitesimal fraction of the number of states that the user can input. It doesn't bother us at all. We're programmers. We're used to that. We work with command line interfaces in compilers, languages, shells, operating systems all the time. We're used to the fact that, sure, you can fire up MS-DOS and say, computer, fix yourself, and it won't respond to that. That doesn't bother us at all. A real person, it should bother. But we're used to the idea that there are all these imaginable states, and you have to find the 3 accessible states that actually do something. That doesn't bother us. We transfer that to our users as an expectation that is utterly inappropriate. When users look at a parser, they see English. They have every reasonable expectation that anything that they can compose in English will work in a parser. And of course, that expectation is utterly, horribly wrong. In other words, parsers vastly expand the number of imaginable states without increasing the number of accessible states. This is the wrong way to design a user interface. Okay, well, I've talked about the negative aspects of it, of compressing the number of imaginable states. Now let's turn to the question of how we expand the number of accessible states. That's more positive. I mean, now we're making our game world better. How can we increase the number of accessible states in a game? Well, at this point, I'd like to observe program trees obviously get a lot of accessible states. How do they do it? What are they doing right that we're doing wrong? And I suppose what I have to do here is take a little bit of a logical jump. What I'm going to do here is we're standing right here on top of game trees, looking enviously in the direction of program trees, saying, golly gee, we'd sure like to be like our big brother there. What can we do to look more like them? And at this point, I'm going to turn 90 degrees and go off in a completely different direction. So stay in with me here. Let's talk about stories, okay? What's a story? Well, let me show you a picture of a story. Here's a story. Once upon a time, there was a geeky nerd named Ned. And one day, Ned met a beautiful woman named Mary. And Ned said to Mary, "Golly gee, chickie, you sure are purty." And Mary, swept away by the towering eloquence and magnificent romanticism of Ned's prose, ripped off her clothes and dragged Ned into bed, and they lived happily ever after. Now that's the story. And the important thing about a story is it is a sequence of events arranged in some sort of temporal or causal order. It is a story. It is a linear sequence of events. And so we call it a storyline as opposed to a game tree. Now the interesting observation I'd like to make about a storyline is that you could think of a storyline as a kind of a species of game tree. An extremely skinny game tree. A game tree with exactly one accessible state. Now, the important observation here then is that a story constitutes the other direction. That is, if we want to get bushier, richer, thicker game trees, what we need to do is stand here in the world of game trees and turn and look at storylines. And look at them very carefully and set our sights on them and get them exactly in our sights, and then turn 180 degrees and run as fast as we can. Because stories are the wrong thing. They are skinny. They are 0 or 1 accessible state. That's the wrong way to do it. Unfortunately, this observation is useless because all it's telling us is what we shouldn't be doing. It doesn't tell us what we should be doing. So how are we going to improve this? Well, at this point, let me put up another diagram. What we have here is the game tree, which is analogous to a program tree. And then we have a relationship here between a game tree and a storyline. That is, in this dimension, a storyline is a very, very skinny game tree. Well, I look at this diagram, and something leaps out at me. When I look at that diagram, I see a great big hole right there. There's something missing. Well, that's the $64,000 question. What belongs in that hole? Ding, 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 ding. Sorry, your time is up. The answer is a calculation. Here, what you do with a 4-function calculator. 27 add 15 equals 42. It is analogous to a storyline in that it is linear. It is analogous to a program tree in that it is computational. Therefore, what we have is this set of relationships here. Now, is there anything we can conclude from this? Well, what I'd like to do now is say, if we could examine this relationship, maybe that would tell us something about this relationship here. Okay, so let me start off with a long analysis of this relationship here. And what I'm going to do is set up a progression from calculation to program tree. So at this end here, we're going to have the type of hardware that you use to calculate with, namely a calculator. And we're going to put at this end the simplest, dumbest 4-function calculator you can buy in Kmart for $5. All it can do is multiply, divide, add, and subtract. The next step up is a 4-function calculator with 1 memory register. In other words, you can say 27 add 15 equals 42. Store that in the memory register, and then later on we'll come back and recall it. The next step up is a calculator with maybe 10 memory registers, one assigned to each key on the keypad, so that you can say store this in register 5 and recall from register 2, something like that. The next step up is a calculator. Now we're getting into a highfalutin calculator with several hundred memory registers. And now you can store into register 142, something like that. The next step up is a huge step intellectually, but a very small step in hardware terms, and that is a calculator with indirect addressing. So you say 142, recall from that register number that I just typed in. So that's indirect addressing. The next step up is a big step in hardware terms, but a very small step intellectually. That's a general purpose 8-bit microcomputer has got 65,000 registers and address bus to refer to them. We've really taken a big leap here. The next step up is my Mac 2 running Microsoft Word with 8 megabytes of RAM and a heap with blocks and pointers and handles, and we program it in a high-level language. Now, what we have here is a progression of hardware from the calculator to the Mac 2. And I'd like to talk about some of the properties of this progression. The first property I'd like to point out is that this progression represents a progression of increasing power. We're moving from the least powerful machine up through increasingly powerful machines until we get to the most powerful machine. So power is increasing. Another observation I'd like to make is that this is a progression of increasing options. The user has more and more options in using the device. This is expressible in two ways. One, what he can say to the device. He gets more buttons. The 4-function calculator has 18 keys. As we move up to bigger calculators, we get more and more keys, till finally we get to the 8-bit microcomputer that might have 60 or 70 keys on a keyboard. Then the Mac 2, it can have hundreds of thousands of keys because each pixel on the screen is addressable with the mouse and can be user interface functional. Therefore, we're getting more and more things that the user can say, more and more ways to express himself, more and more ways for him to select options. The other way of expressing the increasing number of options is that the machine can itself express more options. The 4-function calculator has, what, 8 7-segment LEDs? So it can express 100 million numbers that way. As we move up, we get more digits, which means there are more numbers that we can express. And then we go to multiple rows of digits. And then we go to alphanumeric displays. And then finally, with the 8-bit computer, we're getting 24 lines by 64 characters. We're getting zillions and zillions of possible displays. And then with the Mac 2, we get these high-resolution, big-screen monitors with really zillions and zillions and zillions of possible things that the computer can express. So we're getting an increasing number of options expressible by the computer. Okay, so we're getting more power, we're getting more options. Obviously what that means is more accessible states from the hardware point of view. The Mac 2 can generate more accessible states, more things for the user. That's good. But we're also getting increasing price too. That's not so good. But there's one other very important observation I would like to make, and that is that this progression is also a progression of increasing indirection. That is, as you move up the progression, you're getting more and more indirect in the way you are computing. For example, let's take that 4-function calculator. You have 0 indirection with a 4-function calculator. What do you actually do? You say, 27, there's a number right in front of your face. Add 15 equals 42. As clear, as direct, as explicit as you can get. Now when we move up to the calculator with 1 memory register, now we've injected a tiny amount of indirection. You take that number and then you store it off in a memory register, and now you forget the details of the number itself. You just say, well, the number that was in the memory register, whatever that number was, I'm going to use it later. And so now we're talking about that number indirectly. It's the number in the register. Now, when we move up to the calculator with 10 registers, now we're getting more indirection because there are, first, more registers. And so instead of talking about, in the case of the 4-function calculator, we talk about 42. In the case of this calculator, we talk about the number in the register. Now we're talking about the number in register 8. Then we talk about the number in register 142. Then, with the 8-bit personal computer, we're talking about any of 65,000 memory registers. And then with the Mac 2, we're getting 8 million memory registers, but it's not just quantity of indirection. We're not getting more indirection merely by having more registers. The fact that we're getting larger and larger also implies that we had to increase the intensity of the indirection. Consider, how do we access that number in a Mac 2? Here's the number, 42. What do we do with it? We put it in a memory register. So we got the number, and then we got a memory register. But wait, we don't ever actually talk about the memory register. We talk about the address of the memory register. But wait, we store the address in a pointer. But the pointer is in another memory register, and we have to worry about the address of the pointer. That's kept in a handle, which of course is stored in another memory register, and we have to worry about the address of that memory register, which we keep in a symbol in a high-level language. Now look at all of the levels of indirection going on here. We've really increased the amount, the quality of the indirection in a Mac 2 as much as we've increased the quantity. Therefore, what we've got here is a progression of increasing indirection of use. Now at this point, I'm going to make an intuitive leap. This is not rigorous logic, but I'm going to say, I find the association between increasing indirection and increasing power, increasing number of options, I find that very compelling. And I'm going to suggest for your consideration the possibility that there's a causal relationship, that somehow more indirection necessarily grants more options, more accessible states, more power. So let's explore that possibility. Let's just proceed on the assumption that if we could put more indirection into our games, then we would get more power, more accessible states. So, how can we do that? I mean, practically speaking, what does it mean to put more indirection into a game? Well, there's a simple-minded approach. Let's start off with the first simplest strategy. You will notice that one of the things we got in the hardware progression was increasing number of registers, from 0 registers to 1, to 10, to a couple hundred, to 65,000, to 8 million. We got more and more registers. That's what you do with hardware. But in software, what do you put in registers? Variables. Variables are what the software puts in the hardware. So if the hardware is giving us more and more registers, if we want our software to climb along this progression, we want our software to have more and more variables. Now, what does that mean? Well, let's see if I can, let me at least put this in context. Let's come right down to a real game. Let me talk about a classic adventure game. What kind of things, what kind of variables do you have in a classic adventure game? Well, they're typically Boolean variables representing the types of things that the player is carrying. So the player has the purple key that gets him through the purple door. Is the player carrying the magic scroll of truth, you know, that he reads at the right moment to make something go away? Is he carrying the vial of magic elixir that he drinks to make the princess kiss him? Does he have in his pockets the holy handkerchief, complete with the sacred snot? You know, there are all these things he's got in his pockets, and he goes through the adventure stuffing his pockets and then looking at things and dumping out his pockets. Typical classic adventure, you're talking a few dozen of these variables. Let's be generous. Let's say 50 of these variables. Notice that they are Boolean variables, 1-bit variables. In other words, the classic adventure game might have 50 bits of global state variable. Now, let me first point out that this corresponds roughly to the hardware level of the 4-function calculator with 1 memory register. That's how far we've climbed up this sequence. Microsoft Word is pretty far off on the horizon. Let me put this in another context for you. If you know some mathematics or some thermo or some information science, you'll know 50 bits of information will generate 2 to the 50th accessible states. That may sound like a lot. That's 10 to the 15th, or 1 quadrillion states. And at this point, you may say, come on, Chris, 10 to the 15th accessible states, a quadrillion states? No human being could ever possibly explore all of those different states. That's so many states, it's more than we could ever need. Wrong. Let me give you some comparative figures. Tic-tac-toe generates 10 to the 2 accessible states. Chess generates 10 to the 126 accessible states. The classic adventure generates 10 to the 15 accessible states. That puts it closer to tic-tac-toe than to chess. Let me put it in even stronger terms for you. Let's compare it with a word processor. But hey, I don't want to be unfair here. Let's not compare it with a high-powered word processor like Microsoft Word. Let's handicap the situation a little bit. Let's talk about a word processor that can only generate one page of output. That's its upper limit, just one page. And let's suppose this word processor is so dumb that it puts out monospaced dot matrix output. All it can do is put ASCII text on a page. It can't do different fonts. It can't do different font sizes. It can't do font styles like italic or bold or underline or any of that stuff. It can't change the margins. It can't put tables in or illustrations or headers or footers or any of that other stuff. All it can put is 2,000 characters on one piece of paper. That's it. Now, that's a pretty stupid word processor, isn't it? And you'd have to admit that the thing would not really be usable. But let me point out that such a word processor can generate 10 to the 3,600 accessible states. In other words, on a logarithmic scale, that brain-damaged word processor outperforms a classic adventure by a factor of 200 to 1. Obviously, there is considerable room for improvement. So, we need more variables. But when I say we need more variables, not only do we need to expand the number of global state variables, the factors that you consider in the game. What's the air temperature? How fast is his heart going? What's his shoe size? What's his birthday? More factors like that to consider. Not only must we do that, but we need to increase the size of the variables. You know, so many games I see. How many times you're playing these games and they're so Boolean. Everything is black and white. For example, I'm very pleased to know that a lot of games are finally starting to put characters into them. That is, I'd say for years and years, I used to rant and rave about, we gotta have characters in a game. We gotta have people, not things. And those things weren't what was selling. What was selling was Pac-Man and Space Invaders, and everybody just laughed. Well, at long last, the industry seems to have figured this out for itself. The characters are really good, and we're seeing characters coming into computer games. That's great. That's really good news. I'm pleased to see that. However, the characters we're seeing are one-bit characters. For example, you walk up in one of these games, and you encounter a character, and it tells you all about the character. Hey, wow, this is fun. And the problem is, either you say the right thing or the wrong thing. Now, if you say the right thing, why, then that character is your good buddy, and he puts his arm around you, and he really likes you, tells jokes, he gives you some gold, and he gives you a magic sword, and he tells you how to get past the red dragon down the road, see? But if you say the wrong thing, why, then he pulls out his battle axe and he whacks off your head. He hates you. Well, I hope it doesn't insult anybody's intelligence for me to observe that this represents an oversimplification of human relationships. I mean, we could just as easily have 7 states. You know, he loves you. He likes you a lot. He likes you little. He doesn't really care either way. He dislikes you little. He dislikes you a lot. He really hates you. Now that's 7 states. And may I point out, it takes all of 3 bits to encode those 7 states. Now, is it asking too much, given that our target machines now have at least half a megabyte of RAM? That somewhere in all those bytes, somewhere we could find space for 3 bits of RAM. Surely that is possible. So, we need to broaden our variables, get more bits into our variables, start doing arithmetic rather than Boolean logic on them. Now, that's one thing we can do. More variables, wider variables. Second thing we can do, graphics. In the last few years, we've seen some real changes in computer games. Used to be, you'd go into a store, buy a computer game, take it home, pull out the disk, put it in the computer, and run it. Nowadays, well, we've got a lot more graphics. So now, You go into a store, you buy the computer game, you have the clerk help carry the game out to the car. You take the box home, trundle it into the house, and all you need to do is take your fingernail and just nick the shrink wrap on it. And all of a sudden the box explodes and discs go flying into the air and fluttering down on you. There are discs everywhere, 10, 20, 50 discs, more and more discs all the time. Why? Because all the megabytes of graphics we're putting into these games. I mean, we employ armies of artists to generate all these graphics. Do you know how many forests of magnetic trees we're cutting down? This is really getting out of hand. And what's particularly distressing about it is so completely unnecessary, because all these graphics are direct bit-mapped graphics stuffed right into the game as crudely as possibly. The best thing we ever see is people do some compression schemes. Whoop-de-doo. It is completely unnecessary to be so explicit, so direct. For example, consider that a great deal of the activity in a computer game, in fact in the real world, takes place inside structures, in rooms. Now, consider rooms. Simple things graphically. They always have a horizontal floor, some vertical walls, some windows, doors, furniture, maybe a few things hanging on the walls. That's all it takes. Now, you would think then that you could generate an algorithm to describe a room. And in fact, I just did. I gave you an English language algorithm that describes rooms. And it's not a very good algorithm, but I think you can see that this is a computable problem. That is, if you sat down and worked at it for long enough, you could write a routine that would generate rooms. You'd pass parameters to it, like, size of the room, and then, what type of decorations it's got, and it could generate a room for you, algorithmically. Now, yeah, there'd be some complexities. You'd have to, for example, pass what type of room it is. Well, bedroom, kitchen, torture chamber, and then you'd have to determine from that the type of furniture that's appropriate. Bed, kitchen utensils, rack, whatever. And it would just look all of these things up there. Yes, there'd be some data, but it's mostly algorithms determining how to build this room. Now, I can hear your objections. Come on, Biss. We don't have all the time in the world to go off and crunch numbers for 5 seconds building a room. We got to keep this game moving. We can't afford all day to do this process-intensive approach. Well, yeah, that's true. But how long does it take to load 20 kilobytes of compressed color bitmap off of a floppy disk? In the same amount of time it could take to load all that information in, you can probably generate a pretty fast room, a pretty good-looking room. Next objection. Chris, everybody knows algorithmically generated graphics look dumb. They're mechanical, they're simplistic, little wireframes, stick figures, and so forth. Nowhere near as rich and interesting as what an artist can do. Absolutely true. Because we have 5 artists working on generating mountains of bitmaps, and we have one stupid programmer who gets 3 days to write up the algorithms. Of course the comparison stinks. If you were to have 5 programmers working for a year generating a room drawing algorithm, I can guarantee you will have a lightning-fast room generating algorithm that will generate magnificent-looking rooms. Now, maybe you still can't afford that, but I want to point out it's entirely possible. And it's not just rooms. All kind of graphic objects can be generated algorithmically. There are rules for the way things look. Nature doesn't just randomly slop things onto the canvas of the world. Things exist for reasons, and if you can write those reasons in code, you can get the images on the screen. We can do it. It just takes a little more intellectual effort. So that's the second thing we can do. More indirect level graphics. Third possibility. I'd like to talk about hardwired branching. This is branching that is explicit or direct. Let me give you an example. Let me go back to my favorite whipping boy, the classic adventure game. Here we are. When we last left our hero, you're standing at the edge of a mighty precipice. Far beneath your feet, a raging torrent rips and tears at its gorge. The wind whips, touzles your hair, and whistles in your ears. On the far side of the chasm stands a winsome lass, her hands clasped in entreaty as the virile wind rips and tears her flimsy gown. You can hear her crying out. Just above the wind, you can hear her angelic voice. Help me! Help me! The astute player is able to infer from this that the designer intends for him to cross the chasm. You look around you in vain. There is no bridging materials, no rope, no portable jetpack. What am I to do, you say? Ah, look, not 50 yards away, grazes a winged horse. How convenient. You approach the horse. He runs away. What now? Well, 55 turns ago, while you were in the dark forest, you came across a small cottage whose door was locked. And inside the cottage was a small dark room. And on one wall of that small dark room was a hidden door. And behind that door was a tiny closet. And inside that tiny closet was a chest of 4 drawers. And inside the 4th drawer of that chest was a paper bag. And inside the paper bag was an apple. Now, if 55 turns ago you had broken down the door of the small cottage, broken into the cottage, used your torch to look around, seen the hidden door on the wall, opened the hidden door, gone inside the tiny closet, opened up the 4th drawer of the, found the 4 drawer chest, opened up the 4th drawer, not the 3rd drawer, that's got the poison scorpion in it, opened up the 4th drawer of the 4 drawer chest, looked inside, seen the paper bag, pulled out the paper bag, looked inside the paper bag, seen the apple, grabbed the apple, put the apple in your pocket, kept the apple with you, then, now, you can feed the apple to the winged horse so that the winged horse will feel grateful and fly you across the chasm so you get the girl. What could be simpler? Okay? The problem with this is that it's too direct. I mean, by direct, I mean the designer planned everything out explicitly. I mean, you can see a line of code, you're playing that game, and my eyes glaze over and I'm seeing program code as I'm playing. And there's a line of code that says, if the player gives the apple to the horse, then the horse will fly him over the chasm. This is the wrong way to design computer games. The right way is to have a line of code that says, if the player satisfies the needs of a non-player character, then the non-player character will feel gratitude towards the player. Wait a minute, you say. Just what the hell do you mean by satisfying the needs? What's that? I mean, I'm sorry, I need the hat still on, I'm still you. I have a identity crisis here. I mean, when you talk about giving the apple to the horse, you know what you're talking about. That's direct, that's explicit, that's easy to understand. But boy, all this stuff about satisfying needs, I mean, God, pretty soon start talking about Freud and all that crap. Well, yeah, that's true. It's more indirect to talk about satisfying needs. And you know how you're going to do it? You're going to need to specify the needs of each non-player character. You know how you're going to do that? With a variable called needs of players, an array. And you're going to have to specify, actually an array of records. You're going to need to specify the needs of every non-player character. And you know those needs are variable. After you've satisfied somebody's hunger, their hunger goes away for a while, but then later it comes back. So you're going to need some algorithms to calculate how those needs, those variables, change. You're going to need more variables to specify how you satisfy different types of needs. And you know, for example, the horse has one set of needs, and the winsome lass has another set of needs. And you satisfy them in very different fashions. You better not get them mixed up. You're going to have a lot of variables here. And it's going to be a lot more work. And you're going to have more algorithms and more equations and a lot more indirection. But the end result is that one equation, if the player satisfies the needs of the non-player character, then the non-player character feels gratitude for the player. That equation can work for the horse, and the dragon, and the winsome lass, and every other character in the game. And you can expand it and come up with other things. If the player antagonizes the non-player character, then the non-player character will feel anger in proportion to his temper. You can put in all sorts of stuff in there. And yes, it's going to be complex. Yes, it's going to be indirect. Yes, it's going to be more difficult, but it's also going to be far richer. It's going to have a game tree with more accessible states. That's how you make better games. Thank you. Yes?
Did you consider that in your word processor that the complexity of our language has 26 letters, and that perhaps the game industry, it doesn't have 26 letters yet?
Okay, the question is, did I consider the fact that the word processor has 26 letters and the game industry does not have 26 letters? So the word processor industry has a richer set of tools to work with. Do I interpret you correctly?
Right.
Well, that's true. But let me point out that those 26 letters were not invented by the word processing industry. That is, there's something that we all spend a long time learning. They represent human capabilities, and that's a level we have to rise to. I agree. Designing a language of interface is one of the toughest tasks of game design. And in fact, we can't use all of those 26 letters. We can't do English just yet. So we'll have to design our own languages, and yes, this is going to be a lot of work. But it's still a computable problem. It is still soluble. It is a matter of user interface design. Yes?
Well, I was talking to someone last night, or actually this morning, and they suggested to me that they didn't understand why in Balance of Power and in some other games, Perestroika didn't happen. I mean, you can't get the reality, the rich reality of Perestroika, and I wonder if you'd like to comment on that.
Well, of course, the Balance of Power creates a closed little universe, and it does very well within its universe, and the universe is fairly parallel to the world of 1985. Unfortunately, the world went and changed on me. So now, the universe of Balance of Power has very little connection with the real world. So this is one of the problems of designing a closed universe. Now, yes, I could have designed a broader and richer game if I had more RAM and if I was a better designer and if I could think even more indirectly. That is, in a more indirect level, I would have had equations for how the Soviet Union changes under stress. That would have been even more indirect, even more powerful. I'm not smart enough. Yes?
Something, when you first started, you mentioned your word processor was version 4.0.
Yeah.
And that's something that you can't say too much about very many games. They don't last long enough to go through revisions.
Yeah.
And but that sounds like a kind of a nice goal too, to make a game rich enough it can last for 5 years while people are learning it and improving it and experimenting with it.
Richard Garrett has made a career out of that. You know, yeah, that's a good idea. It works. It makes money. I'm too impatient. You know, I finished one game. I got 200 other games I got to get done, so I move on.
Well, so the market's that way too.
Yeah. Well, not in Richard's case, though. So. Other questions? Yes?
You mentioned using algorithms to generate graphics and to generate decisions.
Yes.
What else can algorithms be applied to do?
Oh,
My immediate temptation is anything you can imagine.
you want a complete list, Chris.
Some more closed answer.
Wait, I'm sorry?
Anything specifically
I
that are particularly, you want to advocate that we...
No, I offered those three examples because those are good, clean cases with clear, very clear things that I can talk about in 5 minutes. I can spew a lot of hot air for several hours about process intensity and how this plays out in many different angles. I'm not prepared to do that right now. Sorry. Other questions? Yes?
You were talking about in a simulation, Battle Britain specifically, that there were a lot of things that you wanted to do that you couldn't do. But it seems to me like in a simulation, the expectations are that you can just fly that plane and that you can do loops or you can do rolls. It's sort of an infinitely variable set of things that you can do.
Well, actually, flight simulators are excellent examples of a good closed universe. That's one reason why I like them. I mean, in a flight simulator, you don't worry about running water. You don't encounter that very much upstairs. So it's a closed universe to start with. It's a visually closed universe. The visual field in a flight simulator is very simple, and so it's always done algorithmically. And so I'd like to hold them up as theoretical, excellent examples of good theory being applied to games. Even then, though, they fail to capture a lot of the realities of air combat. There are just a lot of things missing from Battle of Britain. Things that I would like to do, things that I think I should have a right to do, things that cause me to lose that shouldn't have caused me to lose. I really resent that.
What's an example?
The fact that I can't shoot all my guns at once. I have to jump from gun to gun, and it's hard to figure out where I am. What I'd like, I mean, here I am on one side of the plane shooting that way, and then the plane flies past me, and I want to turn around and shoot the other way. Well, I stop shooting here, and I say, what button number was it? And I always push the wrong button, and I end up shooting the wrong direction. Moreover, my own gunners, I can put my guns on automatic, and they go all over the place, and they never hit anything. So it's really frustrating. They're terrible gunners. So those are a couple examples for you. But you also can't fly into other planes. Unless maybe someone from Lucasfilm might want to correct me, but I've sure tried. And I just right into that plane, and I just end up on the other side. It doesn't work. So, let's see, other questions? Yes?
How was Tetris fit into this?
Ooh, I don't know. Tetris is an extremely simple game, and that is, to some extent, that is certainly a factor in its success. The fact that the designer chose an extremely narrow context. He's going to give a very, very closed universe. It's just blocks fall. That's all. And within that closed universe, he's got everything. It's a complete universe. He completely spans the vector space of the imaginary universe of that game. That's one reason why that game is so satisfying. Even though it's a tiny game, it covers its world perfectly. So, as you try to get bigger and bigger, as you get more ambitious, you start leaving gaps in your program. The most extreme ones are these universe games that purport to have an entire universe in them with populations and cultures and history and technology and so forth. And the game feels like little scattered outposts of features. Here's one here, and here's one over there, with vast reaches of empty space between them. And it's ambitious, but in the end it fails. Yes?
I think in the case you mentioned where you want to have a game with vast scope, where you're dealing with large, complex things, the necessity is to provide abstractions that deal with the spaces in between.
Yes.
And for instance,
Yes.
Balance of Power, you deal with an entire world, and
Yeah.
there's a whole world full of things, but you have abstractions that deal with everything that you need to within the context of the game.
Yes.
So you can have a very good galaxy-spanning simulation of galactic empires, but you have to have abstractions, indirections that deal with the
Exactly.
conditions that are important to that environment.
Yeah, in Balance of Power. If you want to ship troops to a foreign country, you don't show the little ship and the little men marching onto the ship and the ship going off to the country or anything like that. You just say, ship troops, and it deals with it at a very distant level. If you're willing to abstract enough, it works. Other questions? I think we're out of time here. Thank you very much.